So here we'll take a look at a problem from the 2009 AP Calc AB and BC exam. It appeared on both exams that year. And it's a non-calculator question where they give us this table of values to work with. So we've got x values listed and we've got some function values that correspond to those x values listed as well. They're telling us a function is twice differentiable for all real numbers, so two derivatives always exist. And then the table of values above gives us selected values of that function from x's between 2 and 13. Part A is pretty typical of most table of values problems that you've seen on past AP exams. They ask us to estimate f prime of 4. So if we're trying to estimate the value of a derivative, graphically we know that the derivative evaluated at a certain x represents the slope of the tangent line at that x. Well, the way that you probably began to develop the idea of a tangent line was by looking at secant lines. So if we use the slope of the secant line on the interval from 3 to 5, and 4 is smack dab in the middle of that interval of the x-axis, to estimate the value of the slope of the tangent line at x equals 4, that's going to be pretty reasonable. The average slope, the slope of the secant line on the interval from 3 to 5 is going to be pretty close to the instantaneous slope of the graph at the x value of 4. So if you just go ahead and carry out a slope calculation between these two ordered pairs, you're going to have a pretty reasonable estimate. Truthfully, this expression right here, this fraction, without even doing any simplification, will receive full credit on the non-calculator section of an AP exam. If you're in a college classroom, you definitely would be looking to simplify that a little bit, but on the AP exam, you can leave your answer like this. You're kind of running the risk of making a silly mistake if you take it to the end, but if you do take it to the end, you should end up with -3 for that one. Part B asks us to evaluate a definite integral. So the definite integral is kind of a goofy one. It's 3 minus 5 f prime of x with respect to x, and we're supposed to evaluate it on the interval from 2 to 13. And so when I first looked at this, I thought, well, I'm going to break this into two separate integrals, right? A definite integral is a linear operator, so I'm going to do the definite integral of 3 with respect to x from 2 to 13, and then I'm going to subtract off the integral of f prime of x from 2 to 13, but I'm going to have to multiply that by 5, right? So I separated it into two separate integrals. I factored the 5 out in front of that second integral. And now if I just apply FTC part 1, first part of the fundamental theorem of calculus, to both of these pieces, the antiderivative of 3 is 3x. I then need to evaluate that at 13 and 2 and take a difference. So here's what I have for evaluating at 3 and 13 and taking a difference. I can kind of make the same comment I made a couple minutes ago at the end of part A. I could have left this as 3 times 13. I could have left this as 3 times 2 and just a subtraction sign between the two. I did, I guess, run the risk of missing some points here because I was simplifying along the way, but on the AP exam you could have left it unsimplified. And then I have to subtract off the definite integral that's listed here. And I've got my 5 kind of copied down here. What's the antiderivative of f prime? Well, that's f. I would then need to evaluate f at the upper limit of integration, evaluate f at the lower limit of integration, and take a difference. So that's going to be f of 13 minus f of 2. Well, those values are listed for me in the table. F of 13 is 6, so I replaced f of 13 with 6. F of 2 is 1, so I replaced f of 2 with 1. And I simplified further, so as I've mentioned several times already, I could have left this as a great big mess of an expression down here once I pulled the values out of the table that I needed. I did simplify, and I got down to 8, which is the correct answer, but on the actual AP exam, you can leave non-calculator free response question, the results to them, you can leave those pieces unsimplified. In part C here, they ask us to use a left Riemann sum, and the subintervals that we're supposed to use with this sum are indicated by the data in the table, and we want to use that sum to approximate the definite integral from 2 to 13 of f of x with respect to x. So what I took a minute to do here is I took a minute to kind of plot all these ordered pairs, right? So I have all these ordered pairs plotted on my graph here, and I realized, okay, if I'm doing a left Riemann sum, and my first interval goes from 2 to 3 on the x-axis, my first rectangle is only going to have a width of 1 unit. So my first rectangle has a width of 1 unit. What's the left endpoint of this first subinterval of the x-axis? Well, it's 2. I'm going to need to use the function value at 2 to generate the height of that first rectangle. And so f of 2 times 1 is going to give me the area of this rectangle. F of 2 is 1, so 1 times 1 gives me the area of this rectangle here, which is really a square. I'm going to add on to that the area of my next rectangle. Well, my next subinterval goes from 3 to 5. So my next width for a rectangle is 2. So delta x is definitely not constant in this case. We're using delta x as the difference between two consecutive x's as listed in the table. So the first delta x is 1, the next delta x is 2, then we have a delta x of 3, then we have a delta x of 5. So delta x changes with each subinterval here. So for this next subinterval, my left endpoint is 3. The function value at the left endpoint is going to be what I use for the height of that rectangle. So f of 3 is 4. So here's the unsimplified version, and here's after I've taken f of 3 from the table, 4 times 2 for the area of this next rectangle. My next rectangle has a width of 3 units across the x-axis. The height's supposed to come from the function value at the left endpoint. The left endpoint of this subinterval is 5. So the function value there is -2. So my next rectangle has an area of -2 for the height times 3 for the width. And then my last rectangle is going to sit on the portion of the x-axis from 8 to 13. So its width is 5 units along the x-axis. The left endpoint is 8. So the height of that rectangle is going to be 3 units. And so I had 3 times 5 for the area of my last rectangle. I could have left this as my answer. I did simplify a little bit to get it down to 18. On the actual AP exam, your best bet is to leave your answer right here, unsimplified, because if you make some silly computational error across these last few lines, you will get some of the points for the problem, but you won't get full credit. So to save time and points, leave answers like this on non-calculator for your response questions. And then the last question, last part of this problem is kind of a doozy. They ask us to do 2 things, and both things are a little bit time consuming. So I've actually done these on 2 separate slides here. And the first thing that they tell us is that f prime of 5 is 3, and that f double prime of x is less than 0 for all x's between 5 and 8. First part of part D says use the line tangent to the graph of f at 5 to show that f of 7 is less than or equal to 4. And so I saw, line tangent to the graph of f at 5, and so that triggers for me, hey, I need to know the equation of my tangent line at the x of 5. So I need to know the slope of the tangent line at 5. That's going to be coming from f prime of 5. They don't even make us work for that. They give that to us. F prime of 5 is 3. And then I also need the point of tangency. So the point of tangency is going to be the point on the graph of f that corresponds to the x value of 5. Well, that's going to be 5 comma f of 5. Well, 5 comma f of 5 is 5 comma -2. So what's the equation of my tangent line to this graph of f of x at 5? Well, that's right here if I build it in point slope form. Then I have to try to figure out how that tangent line allows me to show that f of 7 is less than or equal to 4. And so they kind of imply that you're going to have to make use of the fact that f double prime of x is less than 0. And if you think about what you've done with second derivatives being negative, you've used that to make concavity arguments. And if the second derivative is negative, that means your graph is concave down. So if your function has a negative second derivative on this interval, the function has got to be concave down on that interval. If the tangent line to that function at 5 has a slope of 3, and the graph of the function is concave down, the tangent slope at 5 is the steepest slope anywhere on this interval. And what that's going to mean is it's going to mean we see a slope of 3 at this point of tangency, but then the slope of the tangent line is beginning to level off. If the graph is concave down, that means the slope of the function is decreasing. And if the slope of the function is decreasing, that places our curve below the tangent line. Well, check this out. If we actually piece together the tangent line from the point of tangency, 5 comma -2, rise of 3, run of 1, since our slope is positive 3, we get to this ordered pair at 6 comma 1. Well, if we rise up 3 more and run over 1 more, this ordered pair right here is going to be 7 comma 4. Well, if that's the point on the line at the x of 7, there's no way that the point on my curve at the x of 7 is going to be anywhere near that high, because in order for the curve to be concave down, my curve has to drop below the point of tangency, or below the tangent line on this stretch of the x-axis. And so my diagram depicts that. And so since the point on the line at 7 has a y value of 4, and my curve has to be beneath the line at that x, I know that my y value on the curve has to be less than my y value on the line at that x. Second part of part D is similar, but now it's requiring for us to use a secant line. And so a secant line has 2 points that sit on the function, and the 2 points that sit on the function that we're supposed to use are the point on the function at 5 and then also the point on the function at 8. And we want to use this secant line to show that f of 7 is greater than or equal to 4/3. So I started by building the equation of my secant line. So the slope of my secant line is going to be whatever the slope of the line connecting these 2 points is. And so that's the calculation that you see right here. So I got 5/3 for that slope. I can use either of these ordered pairs to build the equation of my line, since both of them are going to be present on the secant line. I use the one that's here, so I got y minus -2, so y plus 2 equals the slope that we just found times x minus x1, x minus 5. So here's the equation of that secant line. Now, we still know that the function has to be concave down on the interval from 5 to 8, since the second derivative is negative. If I draw my secant line in from the point 5, -2 to the point 8, 3, and I draw a curve that goes through both of those points that's concave down, what's that got to mean about our curve? Well, our curve is actually going to sit up above the tangent line. And so look at the y values on the line and on the curve at 7, right? This is where x is 5, this is where x is 8, so 7's right here. The y value on the line at 7 is definitely going to be down beneath the y value on the curve at 7. So if we find the y value on the line at 7, we know the y value on the curve has to be a little bit above that. And so what's the y value on the line at 7? So I just put 7 in place of the x in the equation of the line, simplified a little bit, and as I did, I got 4/3. And since we're arguing right here with the graph, and then also in the sentences, I guess it's only one sentence, in the sentence I wrote out here, that the y value on the line has to be beneath the y value on the curve, we know that the y value on the line has to be less than whatever the y value on the curve is at 7.